Here's an example of using Newton's law in two dimensions. So your car is stuck. Instead of using a pulley, you're going to tie a cable directly to a tree, make it taut, and then pull perpendicularly to the cable. What sort of leverage do you get on the car? In this example, you're pulling with a 10,000 Newton tension force, and the cable is taut at 2 degrees. So to do this, we're going to assume at this moment everything is at rest, and we want to find a place to use Newton's laws. I'm going to look at this vertex where the cables are attached. Now I want a free body diagram where I can analyze the forces. So I set myself up a couple coordinate axes so I can identify the angles. So I have a tension force that's down, and then I have two other forces going to the right and to the left. So I call them the tension force to the right and the tension force to the left. Each is at an angle theta from the horizontal, which I know to be 2 degrees. So I have a free body diagram, and now I want to apply Newton's laws. To do that, I need a coordinate system, and so I've identified positive x to the right and positive y up. Newton's second law says the vector sum of all the forces is equal to the mass of the object times the acceleration of the object. I like to stack this vertically because then I can write out my vectors and components. This is a nice way to do it because you can keep everything straight, and it allows you to translate the vector nature of Newton's second law into scalar relationships. So the first force is the tension force that you're applying to the cable. The x component is 0 since it's entirely along the y-axis. So I have its magnitude along the y, and it's in the negative y-axis, and so I use the minus sign. When I do these problems, I like to include the magnitudes of the vectors here, which are always positive numbers, and then always go to my free body diagram and my coordinate system to come up with the right signs. Okay, now let's look at the tension force to the right. I need to find its components along the x and y axis. To do that, I draw a line from the tip of the vector to one of the coordinate axes such that it makes a right angle. The hypotenuse is the magnitude of this vector. Then the lengths of each of the sides of the triangle are the components of the vector along the x and the y axes. And I calculate the lengths, which are positive numbers, and then I determine the signs by the free body diagram in the coordinate system. So in this case, the x component is the magnitude times cosine theta, and the y component is the magnitude times sine theta, and they're both in the positive x and y axis given this coordinate system. So what about the tension force to the left? Same idea. I draw a line from the tip of the vector to one of the axes such that it makes a right angle. The magnitude is the hypotenuse, and the lengths of the sides of the triangle are the components in the x and y direction. The lengths of the triangle, then, t sub l cosine theta for the x component, and TL sine theta for the y component, those are the sides of this triangle, and then given the coordinate system, I notice that the x component is pointing in the negative x direction, and the y component is pointing in the positive y. The mass times the acceleration in vector form, which is just the mass times the x component of the acceleration, plus the mass times the y component of the acceleration. And now I can translate this vector relationship into scalar equations I can solve because the sum of all the x components is equal to the x component of ma, and the sum of all the y components of the vector forces is equal to the y component of the mass times the acceleration. Here are the x components. Now I know nothing is moving, so that the acceleration in the x direction is 0. Using this, I can establish a relationship for the right tension and the magnitude for the left tension, and I can find that the magnitudes are the same. So I can just call that the tension in the cable, which I'll call T sub c. Looking at the y component, I have this relationship, but again the acceleration in the y is equal to 0, so now I can solve for the tension in the cable, which is the tension that is pulling out my car. Solving that in terms of the tension that I'm pulling on the cable, I get the tension in the cable is equal to the perpendicular tension that I'm pulling on it divided by 2 sine theta. Now remember, sine theta is small, so when I plug in those values, I get a tension in the cable of 143,000 newtons. That's more than an order of magnitude larger than the tension that I'm pulling. Now you might think, does this make sense? And maybe it doesn't, that seems too large. But we can double check that to find that it's right. And this is why you should never do this. If your car is stuck really badly and you try to pull it out with another car, maybe your tires will spin and it won't come out. If you try this technique, this is a good way to snap your cable, or your chain or rope or whatever. And if it snaps under these enormous tensions, it could do serious damage or even hurt someone. So this is a dangerous technique because the forces you get are too large.